Welcome back to the All Sorts podcast, where we kind of take your curiosity as our compass, and we dive deep into fascinating corners of knowledge. Today, we're going to strap on our hard hats and venture into the world of structural analysis.
Oh, very exciting.
It is. We're going to tackle cantilevers and one-way slabs.
Yes. These are the often unsung heroes of the built environment, I would say.
You're right. We see them every day. We don't often think about them.
Right.
But you've provided some amazing research papers, design guides, and practical examples. So by the end of this deep dive, not only will you understand how these structures work, but you'll have a newfound appreciation for the minds that figured it all out.
Sounds like a plan.
All right, so before we get into the nitty-gritty, let's make sure we're all on the same page.
Okay.
Can you give us a quick, jargon-free definition of what exactly a cantilever and a one-way slab are?
Yeah. So think of a diving board extending out over a pool, anchored only at one end. That's the essence of a cantilever, a structure that's supported at only one end, with the other end free to move. Now, imagine that diving board was made of concrete and extended across a whole room, supported only by the walls on two sides. That gives you a basic idea of a one-way slab. It's a flat structural element that spans between two supports and mainly transfers the load in one direction, perpendicular to the supports.
Okay, I'm starting to get it. But
Ooh.
why a one-way slab? What makes it different from other types of slabs?
Great question. It all comes down to how the load is distributed. Think about that diving board again. The weight of the diver primarily travels along the length of the board towards the support. In a one-way slab, it's similar. The load travels across the shorter distance to the supports on either side. There are also two-way slabs,
Right.
which are supported on all four sides and distribute the load in multiple directions. But those are a story for another deep dive.
Okay, got it. So one-way slabs are designed to handle loads primarily in one direction, kind of like a series of beams placed side by side.
Exactly.
But let's go back to cantilevers for a second. They seem to defy gravity. How do they manage to support weight without just snapping off?
It's all about a delicate dance between material strength and clever geometry. The material itself, whether it's steel, concrete, or even wood, needs to be strong enough to resist the bending forces created by the load.
So a stronger material equals a longer cantilever.
Exactly. But the shape is equally important. Think about that diving board again. It's thicker at the base where it connects to the pool deck and tapers toward the free end. This isn't just for aesthetics. That thicker section helps to handle the higher stresses that occur near the support. Engineers carefully calculate these shapes to ensure that the cantilever can safely support the intended load.
So I'm guessing the length of the cantilever also plays a role.
Of course.
A longer cantilever would probably deflect more under the same weight, making it more prone to failure, right?
You're spot on. There's a limit to how far you can extend a cantilever before it becomes unsafe. And that's where things get really interesting. We actually have a research paper here that delves into a fascinating aspect of these structures. It's called PDF, Behavior of One-Way Reinforcement Concrete Cantilever Slabs with Openings.
Ooh, openings. That sounds intriguing. Why would you want to put openings in a cantilever or a slab in the first place?
Well, in the real world, you often need openings for things like, windows, doors, or even ductwork.
Sure.
But creating those openings introduces a new set of challenges for engineers.
I can imagine it's like poking a hole in your diving board.
Big
Probably
time.
not going to be as strong. But how much of an impact do these openings actually have?
That's exactly what this research paper explores, and the findings are pretty eye-opening.
Okay, I'm hooked. Tell me more.
Well, the research specifically focused on one-way reinforced concrete cantilever slabs. They tested these slabs with different types of openings, squares and circles, and what they found was that both the shape and size of the openings could significantly impact how much weight the slab could handle and how much it would deflect under load.
So a small window opening wouldn't have the same effect as, say, a large doorway.
Exactly. The larger the opening, the more pronounced the impact. They even found that a cantilever slab with two circular openings could experience a decrease in its ultimate load carrying capacity by as much as 31.28% compared to a solid slab. That's a pretty substantial reduction in strength.
Wow, that's way more than I would guessed. So it's not just about whether there's an opening, but also the shape and size of that opening, making me rethink all those times I've casually grilled holes in walls for shelves.
Don't worry, those small holes are unlikely to bring your house down. This research is more focused on the larger openings that are common in structural elements, but it does highlight the importance of careful design considerations when you're dealing with openings in load-bearing structures.
That's definitely reassuring. So is there anything else from the research that stood out to you? Any other key findings we should highlight?
Absolutely. One of the most fascinating findings was that the location of the openings matters a lot. Openings that are closer to the supports tend to have a greater impact on the strength of the slab compared to openings that are further away.
That's interesting. Is there a reason for that?
Think back to what we talked about earlier with the diving board. The stresses are highest near the support where the board is anchored to the deck.
Right.
The same principle applies to slabs. The areas near the supports experience the highest stresses, so any discontinuity in those areas, like an opening, can have a more significant impact on the load-carrying capacity.
So it's all about where the stress is concentrated. Makes sense. But it also makes me wonder, how do engineers take all of these factors into account when they're actually designing these slabs?
That's a great question. And it leads us perfectly into the next part of our deep dive, where we'll explore some real-world examples of how engineers analyze and design one-way slabs, taking into account all these intricate factors.
I can't wait to unpack that. All right, so we've talked about the theory behind cantilevers and one-way slabs, and we've even touched on some of the challenges that openings can create. But now I'm really curious to see how all of this translates into actual design and analysis. You mentioned we have some real-world examples to work with.
Yes. You provided some fascinating material that shows exactly how engineers approach these calculations in practice. It's like peeking behind the curtain to see the magic happen.
Okay, so let's imagine we're tasked with designing a one-way slab for a typical floor in a building.
Yeah.
Where do we even begin?
Oh, just like any good detective, the first step is gathering information. We need to know the span of the slab.
Okay.
That's the distance between the supports, the types of loads it'll be subjected to, and the material properties of the concrete and steel we'll be using.
So it's all about understanding the context before diving into the calculations. We need to know what the slab will be up against, literally.
Precisely. Once we have all that information, we can start crunching some numbers.
Okay.
One of the key things we need to figure out is something called bending moments.
Ah, yes, bending moments. We talked about those earlier. It's the force that makes the slab want to bend under load, right?
Exactly. Imagine you have a ruler held horizontally between your two hands.
Okay.
When you press down on the middle of the ruler, it bends, right? That's bending in action. And the bending moment is a measure of how much that ruler wants to bend at any given point along its length.
Okay, I see. So in a slab, the load is like the pressure on the ruler and the supports are like your hands.
Exactly.
And the bending moment tells us how much force the slab is experiencing at different points along its span.
You got it. And we also need to consider another force called shear force.
Okay.
This one acts perpendicular to the slab, trying to slice it apart. Think of it like cutting a piece of bread with a knife.
Okay, so bending makes the slab curve and shear tries to cut it.
Yeah.
Got it. But how do engineers actually calculate these forces? Sounds pretty complicated.
It can be. But engineers have developed some clever methods to simplify the process. One common approach is to use formulas based on beam theory. These formulas take into account factors like the span length, the load type, and the support conditions.
And this is where that trick of analyzing a 1 meter strip of the slab comes in handy, right?
Yeah.
You mentioned it earlier.
Exactly. By analyzing a unit strip, we can apply those beam theory formulas to calculate the bending moments and shear forces at different points along the slab. It's a way to break down a complex problem into smaller, more manageable pieces.
Okay, so we've gathered our information, calculated our forces using beam theory, and now we know how much the slab wants to bend and shear at various points. What happens next?
Well, the next step is to figure out how much steel reinforcement we need to provide. Remember, concrete is great at resisting compression, but it's not so good at resisting tension,
Right.
that stretching force we talked about. Steel, on the other hand, is excellent at handling tension.
So it's like a tag team. Concrete handles the squishing, and steel handles the stretching.
That's a great analogy. And by embedding steel bars within the concrete slab, we give it the strength it needs to handle both types of forces.
But there's more to it than just throwing in some steel bars, right?
Right.
The placement and arrangement of the reinforcement must be important too.
You're absolutely right. Engineers have to carefully consider factors like the spacing of the bars, the diameter of the bars, and even how the bars are bent or hooked at the ends. It's all about making sure the steel is in the right place to do its job effectively.
So it's like a strategic game of steel placement. You have to put the pieces in the right spots to create the strongest possible structure.
That's a great way to think about it. And it's not just about strength. We also need to make sure the slab doesn't deflect too much under load.
Deflection, you mean like sagging in the middle?
Exactly. Even if a slab is strong enough to support the weight, we don't want it to sag so much that it cracks or feels bouncy and uncomfortable to walk on.
That makes sense. So how do engineers prevent excessive deflection?
Well, there are a few things they can do. One approach is to increase the thickness of the slab. A thicker slab will be stiffer and deflect less under the same load.
But wouldn't that make the slab heavier and more expensive?
It would, so it's always a balancing act between strength, cost, and practicality. Another option is to use higher strength concrete or steel. Stronger materials can handle higher stresses and deflect less, which might allow you to use a thinner slab overall.
So it's a trade-off. Stronger materials cost more upfront, but they could potentially save money and resources in the long run.
Exactly. And engineers also have to consider the support conditions. A slab that's more rigidly supported at its edges will deflect less than one that's simply resting on supports.
Wow, there are a lot of factors to juggle. It sounds like engineers have to be part detective, part mathematician, and part artist to get all of this right.
That's a fantastic way to put it. They need a blend of analytical skills, creativity, and practical knowledge to create structural designs that are both safe and efficient.
This is making me appreciate all the invisible work that goes into the buildings we use every day. It's like there's this whole hidden world of calculations and considerations that most of us never even think about.
You're absolutely right. And speaking of hidden worlds, let's take a brief detour into the past. Did you know that both cantilevers and slabs have been used in construction for centuries? Their evolution over time is a fascinating reflection of advancements in materials, engineering knowledge, and construction techniques.
Oh, I love a good historical tangent. Tell me more.
Well, some of the earliest examples of cantilevers can be found in ancient structures like temples and tombs. The Egyptians, for example, used cantilevered stones to create the impressive cornices and roof structures of their temples.
So they were using cantilevers to create those dramatic overhangs without the benefit of modern engineering tools and calculations.
Exactly. They relied on a combination of skilled craftsmanship, trial and error, and a deep understanding of the properties of stone.
It's mind-boggling how they achieved such feats with the limited resources they had. What about slabs? How have they evolved over time?
Slabs have also come a long way. Early slabs were often made of simple materials like wood or stone, and they were relatively limited in their span and load-carrying capacity. They had to be quite thick and heavy to support even modest loads.
So it was the advent of reinforced concrete that really revolutionized slab construction.
You got it. Reinforced concrete, which emerged in the late 19th century, was a game changer for both slabs and cantilevers. It allowed for thinner, lighter, and more durable slabs that could span greater distances. And as our understanding of concrete technology advanced, we saw the development of pre-stressed concrete slabs, which offer even greater strength and flexibility in design.
It's amazing how the history of these structural elements mirrors the progress of human civilization. It's a story of innovation, problem solving, and the constant quest to create structures that are both functional and aesthetically pleasing. But I think it's time to bring our deep dive back to the present and connect all this knowledge back to our listener.
Sure.
Why should they care about cantilevers and one-way slabs?
That's a great point. It's not just about marveling at ancient temples or Roman aqueducts. Understanding these basic structural elements can give you a deeper appreciation for the built environment around you.
So it's like having a secret decoder ring for the world of construction.
Exactly. The next time you walk into a building, take a moment to look up at the ceiling or down at the floor and try to identify the one-way slabs. Notice how they span between the beams or walls, and think about how the loads are being transferred. Or, the next time you're on a balcony, consider the cantilever that's supporting you and the forces that are at play.
It's like seeing the world with new eyes, noticing the hidden structures that hold everything together.
Precisely. And this knowledge can also be practical. Let's say you're planning a home renovation project that involves removing a wall. Understanding how loads are transferred in one-way slabs can help you determine if that wall is load-bearing and if you need to take special precautions during demolition.
So this knowledge could literally save you from some costly and potentially dangerous mistakes.
Exactly. Even if you're not planning any major renovations, understanding these concepts can help you be a more informed homeowner or citizen. When you hear about infrastructure projects like bridges or tunnels being built or repaired, you'll have a better grasp of the engineering challenges involved.
That's a great point. It empowers you to participate more meaningfully in conversations about the built environment and infrastructure investments. But before we go too far down that road, let's circle back to that research paper about the impact of openings on slab strength. We talk about how the location and size of openings can significantly affect the strength of the slab. But how do engineers actually deal with this in real-world designs?
That's a crucial question. Remember, in real-world construction, we often need openings for things like windows, doors, and ductwork.
Right.
So engineers have to find ways to compensate for the loss of strength that these openings create. One common approach is to add extra reinforcement around the openings.
So it's like giving the slab a little extra muscle where it's needed most?
Precisely. By strategically placing additional steel reinforcement around the openings, engineers can help to redistribute the stresses and ensure that the slab can still safely support the loads.
It's like a delicate balancing act, isn't it? Trying to create a functional and aesthetically pleasing space while also ensuring that the structure is safe and sound.
Absolutely. And that's what makes structural engineering such a fascinating field. It's a constant interplay between creativity, practicality, and a deep understanding of physics and materials.
It's making me look at the buildings around us in a whole new light. I never realized how much thought and ingenuity goes into every detail.
Well, I'm glad to hear that our deep dive has sparked your curiosity. And speaking of sparking curiosity, I think we have just enough time to touch on one final thought-provoking idea. We've talked a lot about how openings can weaken slabs, but what if we flip that concept around? What if we can strategically use openings to actually enhance the performance of a structure?
Whoa, hold on. Are you saying that openings can be a good thing? I thought they were always the enemy.
Not necessarily. Think about how architects use skylights to bring natural light into a building, or how engineers use strategically placed openings to create lighter and more efficient structures. By carefully considering the placement, size, and shape of openings, we can actually manipulate the flow of forces and create structures that are both innovative and sustainable.
That's mind-blowing. So it's not just about mitigating the negative effects of openings, it's about using them creatively to our advantage.
Exactly. It's a reminder that engineering isn't just about solving problems, it's also about finding elegant solutions and pushing the boundaries of what's possible.
Well, that's an inspiring thought to end on. We've covered so much ground in this deep dive. We started with the basics, explored the physics of cantilevers and one-way slabs, delved into real-world design considerations, and even took a quick trip through history. I don't know about you, but I feel like I've gained a whole new level of appreciation for these unsung heroes of the built environment.
I agree. It's been a fascinating journey of discovery. And for our listeners out there who are eager to continue exploring the wonders of structural analysis, we encourage you to check out the show notes for links to the research paper and design guides we discussed today. There's a whole world of knowledge waiting to be discovered.
And if you enjoyed this deep dive, be sure to hit that like button and subscribe to the All Sorts podcast on YouTube so you don't miss out on future episodes, where we'll be tackling all sorts of fascinating topics. We've got deep dives into everything from the history of philosophy to the science of cooking to the mysteries of the universe.
And to stay connected with our amazing community of knowledge seekers and lifelong learners, be sure to follow us on X, Instagram, and Threads. We share all sorts of thought-provoking content and behind-the-scenes peeks at what we're working on.
So join us on this grand adventure of learning and discovery. We're so glad you're here with us.
Until next time, stay curious, keep those minds engaged, and never stop exploring the wonders of the world around us.
It really is, and it's a reminder that learning doesn't have to stop here.
That's right. We encourage you to keep exploring, keep asking questions, and keep marveling at the ingenuity of the built world around you.
Exactly. And speaking of keeping the learning going, if you enjoyed this deep dive into the world of cantilevers and one-way slabs, be sure to hit that like button and subscribe to the All Sorts podcast on YouTube so you don't miss out on future episodes.
And don't forget to leave a comment below letting us know what other fascinating topics you'd like us to explore. We have a whole library of past episodes on all sorts of intriguing subjects just waiting to be discovered.
That's right. We have deep dives into everything from the history of philosophy to the science of cooking to the mysteries of the universe. There's something for everyone at the All Sorts podcast.
And if you want to stay connected with our amazing community of knowledge seekers and lifelong learners, be sure to follow us on X, Instagram, and Threads. We share all sorts of thought-provoking content and behind-the-scenes peeks at what we're working on.
So join us on this grand adventure of learning and discovery. We're so glad you're here with us.
Until next time, stay curious, keep those minds engaged, and never stop exploring the wonders of the world around us.